In this section, we'll talk about aldehydes, ketones, their naming and synthesis. Here we are explaining different uh, functional groups. Like for aldehyde, you have CHO. You can see that carbonyl group, but there is one hydrogen. In ketone, you have two carbon on two sides of carbonyl carbon. In case of carboxylic acid, you have C double bond O OH. These are extremely important families of compounds in organic chemistry, so make sure you know them and recognize them. At the bottom, you're seeing how carbon gets positive charge. Since oxygen is from right hand side of periodic table, it's more electronegative and it pulls electron away from carbon, so there is a movement of electron towards oxygen, for which oxygen gets delta minus and carbon gets delta plus. In addition, the angle is 120 degrees because of sp2 hybridization. Just like naming of any organic compounds, you get the longest carbon chain that must contain the functional group. In this case, is carbonyl group. So in case of aldehyde, it must contain the carbon that has aldehyde group. So for example, the longest chain of this has 3 carbon atoms. So remember, for 3 carbon, one carbon is methane, ethane, propane. So this is propane, but since it's an aldehyde, so it'd be propanal, Al for aldehyde. In case of ketone, the ending would be ONE. So if you look at this longest chain of carbon, there are 6 members, 6 carbon in that longest chain. So 6 carbon means for saturated hydrocarbon be hexane. But in this case, it's a ketone, should be hexanon. Now, we then also look at it more carefully that there is a double bond, C double bond C. So there is an alkene group. So hexenon. And now you need to write down location of the double bond, carbon-carbon double bond, as well as the functional group. The functional group ONE has to get the smallest possible number. So our numbering starts from right hand side, so that carbonyl group gets 2, because that's our functional group. That's how we are naming this compound. So once you have 1 on the far right, then accordingly you'd see carbon-carbon double bond gets 4. So hex 4 in, 2 on. Now let's go over a number of problems from the book. It's on page 318, 9.25. We're going to draw dinitrobenzaldehyde. Now benzaldehyde, that's a common name. Make sure you know what benzaldehyde is. So I strongly suggest that you know these common names, because in exam, in order to find those names, you'd be spending your time unless you know exactly what stands for benzaldehyde. So you have a benzene ring, and you'd have CHO. That benzaldehyde. And this carbon must have 1. So let's number it, number rest of the carbons in the ring, 3, 4, 5, 6. In this case, it's identical no matter whether you're drawing to the right or drawing to the left. Now I need to stick in nitro group to benzaldehyde, and in the third and fifth location. In the third location, there is one nitro group, NO2, and the fifth location, there'll be another NO2. And keep in mind this bonding is through nitrogen. So this gives you 3,5-dinitro-benzaldehyde. Next, we are going to discuss how to write down a structure of 2,2,4,4 tetramethyl pentan 3-on. if I were you, I'd first write down the end part. Always in writing a structure from name, first focus on the end part and forget the 3. So if I forget 3 for the time being, it would be pentanon. So I know from pentan there'd be 5 carbon. So just write down 5 carbon. 1, 2, 3, 4, 5. And I can start numbering from any end, doesn't matter. 1, 2, 3, 4, 5. So I numbered this longest chain. Now what I'm going to do next is going to stick in the functional group, ketone group, and the third location. So ketone group is C double bond, you know that. So that's C double bond O, and you need to have 2 C's on 2 sides. So that's ketone group that gives pent 3-on. And now we have 2244. So I have 2, this is the methyl group, other methyl group, 2, 2, and 4, 4. Keep in mind they all have hydrogen, and you need to stick in hydrogen if you want by considering the fact carbon must have 4 bonds. So each of these carbon at the end must have 3 hydrogens bonded. So make sure you recognize that. So this is basically the structure for 2244 tetramethyl pentan 3-on. Now let's try butane dial. Again, dial means there are 2 aldehyde groups. You know that aldehyde group can only be at the end of a chain structure. You cannot have CHO in the middle. I mean, when it's part of the long chain. So let's get butane first. 3, 4, that's butane. Now butane dial, C double bond O, H. Here also you'd have C double bond O, H. Okay, I think I got a little messy here, so I'm trying to fix it. C double bond O, H. I hope you understand that. And this is let's rewrite this. 1, 2, 3, 4. C double bond O, H. C double bond O, H. So that's the structure of butane diol. Some of the names you need to know as substitution groups, like C double bond O, when it is a substitution group, it's called oxo. And in the same way, you have other groups, acyl, formyl, aryl. Now, accordingly, you can see that this whole compound is named. This is ester, C double bond O, O, CH3. So here we are using oxo, 3-oxo, because it's saying this as functional group, oxo pentanoate. And this group is called benzoyl. Among all these substitution groups you see on this page, this is very important. In many common compounds, you have benzoyl group. So make sure you know that. And also acyl is also important. Now when CHO is attached to a ring, it's called carbaldehyde. So for example, this one will be called cyclopentane carbaldehyde. Now at the bottom you're seeing common names, and I would like you to know each of these common names. So acetone, acetophenone. Acetophenone has a benzene ring as well as CH3, and there is a carbonyl group in middle. And in benzophenone, you have 2 benzene ring on 2 sides of carbonyl group. So that's benzophenone. Make sure you know these structures. Now, synthesis of aldehydes and ketones. We discussed that before, so this chemical reactions will be coming back. Now, if it is 1 degree alcohol, if I want to stop it at aldehyde stage, I'll have to use a very mild oxidizing agent. PCC, which is called pyridinium chlorochromate, which was popular in the past, but in recent days, this new compound is quite common. Pyridinane. So pyridinane, in presence of CH2Cl2, would oxidize an alcohol, 1 degree alcohol, to an aldehyde. Normally, oxidizing agents would change 1 degree alcohol to carboxylic acid, but PCC or pyridinane would stop it at aldehyde stage, for which you need to remember this. Now, if I have a 2 degree alcohol, of course it cannot go much farther, but anyway, I can use PCC or pyridinane, or even more stronger oxidizing agent like chromic oxide, which we discussed before. So there is only one possibility here. This H would go with this H, and then there'll be a double bond formation in here, and that's what you see here, ketone formation. We discussed this reaction under alcohol. Now, this is an alkyne group. So, and this is longest chain, has 4 carbon. That's why it's butane. So it's 1 butane. And in presence of acidic water, so you have H3O plus there, water gets bonded as H plus and OH minus, and use Markovnikov's rule. So I'm just showing water as HOH, and H goes to that carbon, which carbon with unsaturation and largest number of hydrogen. So obviously H goes to this carbon and OH goes to the other one. This is nothing but Markovnikov's rule applied to a triple bond. So now that would result in CH2 on this end, right hand side end, and C double bond COH on this, on the other carbon. Now this is called enol. En is coming from alkene, ol is alcohol group. So there are 2 functional groups present here, alkene functional group and alcohol or OL functional group. And that's why it's called enol. Now pair of electron in between oxygen and hydrogen would make a double bond here, and then this carbon would have too many bonds, 5 bonds, so it will have to break one of its bonds, and it does. The pi bond, it releases electron in the pi bond onto this carbon at the end. So what you get, we haven't shown you that step prior to the final product, is the following: C, 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 double bond O, and then CH2, since electron pair was here, is minus. Then that H plus that came out of here, that H plus goes in there. So this H plus would come over here, and you finally get this compound. This is called enol keto tautomerism. It's not resonance, because in resonance atoms don't move. In this case, atoms do move from OH to carbon. So you can see here, this hydrogen has moved from COH to the carbon at the very end. So we finally get this product. So this is butanol. You don't have to say butan 2-on because it's only one butanol possible. Next, we're going to talk about Friedel-Crafts acylation. And again, this is also something that we discussed in when we talked about reaction of benzene. So I just wanted to remind you that in presence of AlCl3, this Cl will be taken up by AlCl3. That becomes AlCl4 minus, and then there is a positive charge developed here. Positive charge, when developed, is always attracted towards benzene ring. So benzene's double bond would show attraction for this positive charge, and basically it would be attracted to that positive. And finally, Cl, of course, Cl already left, and then you have this compound, acetophenone. Again, the mechanism of this reaction was described under reaction of benzene.